Hello everyone. So I'm going to discuss the topic long short-term memory as part of this deep learning seminar. Long short-term memory or LSTMs are an extension of recurrent neural networks. So let's first talk about RNNs before going into LSTMs. RNN is a neural network specialized for processing sequence of values, so sequential data, for example text sequence prediction. So what enables RNNs to perform this is a feedback mechanism whereby the output of each time step is fed to the next time step. A hidden state in an RNN is represented using this equation h of t, the current time step, where f is an activation function which is applied on an affine transformation on the output from the previous time step ht minus 1 and the input from the current time step, and theta is a set of parameters which is used for the affine transformation, and f is an activation function. And this is how a simple RNN looks, and this is how it looks if we unfold it. So and the black square depicts a time delay here. When we unfold it, we can observe that at each time step there is an input and then which is fed into the network, and the output from that time step is fed forward to the next time step. Now mathematically this can be represented using a function which is performed over all the inputs starting from the first time step through the t time steps, and a function performed over it. Now, why LSTMs? Let's talk about the motivation behind introduction of LSTMs. So RNNs suffer from the problem of vanishing or exploding gradient. So what is vanishing or exploding gradient problem? So let's discuss this using a simple neural network which is given here. It consists of just 3 neurons, and W1, W2 and W3 are the weights between these connections. So we all know that weights, the learning procedure, or the weights are increment to weights is learned through the procedure of backpropagation or backpropagation through time. So we know that the gradient of loss, gradient of the final output, the derivative of loss with respect to the final output can be directly calculated because the loss itself is calculated in terms of the final output. So for the weight matrix W3, the gradient can be calculated using a simple chain rule, which is the derivative of loss with respect to the final output and the derivative of final output with respect to W3. The f is here an activation function, and Z3 is the affine transformation performed in the final neuron. So this is the simple equation which is used to compute the gradient for W3. So this is quite straightforward, and but what happens is when the gradient has to be computed for earlier layers, when for earlier weight matrices, it is a much longer chain because it has to propagate all the way through towards the initial state, and it involves multiplication, involves computation of a lot of derivative, and in addition the activation functions which is used usually are sigmoids or softmax, which involves exponents, and the derivatives of these functions are usually very small in fractions. So if we multiply together a lot of fractions, the resulting number will be very small. So what the consequence of this is that the learning rates for the initial stages will be very small, while the learning rates for final layers will be large enough. So with this is why the challenge of long-term dependencies arise. So because of the vanishing gradient problem, this learning rates for the earlier layers will be very small, while the learning rates for small-term interactions are much larger. So when we have applications whereby we require the context to be inferred from a very early stage, for instance when we are performing a time series analysis or a language modeling problem, then we required information to be inferred from a very early stage. So RNN fails here. So this is why we needed a modification of RNN. A few initial strategies were proposed to overcome this problem. The first strategy was adding a skip connection. Adding a skip connection is basically just adding a connection between a past layer, very distant past layer, to the current layer. Let's say we skip D connections between a distant past layer and the current layer. This means that the gradient diminishes at a smaller rate compared to when the skip connection did not exist. This was one strategy proposed, and another strategy proposed was removing the connection altogether. So removing the connection and then replacing it with a longer connection. And yet another strategy proposed was that of the leaky units. In leaky units, in addition to the usual computations, there is an additional computation, additional updation occurring at each cell. This is the accumulation of the learning which is obtained up until now. So mu t is the learning that has been information that has been accumulated up until the time step t. Mu t minus 1 is the information that has been accumulated up until time t minus 1, and Vt is the current information. So with this equation we can observe that according to the value of alpha set, we can decide to what extent the previous information should be retained and current information should be taken in. This was the strategies, initial strategies proposed. Now, but yet again, if strategies such as leaky units are used, the value for alpha has to be manually set, and this might require a lot of extensive domain knowledge. Now, then long short-term memories came into existence, and this was much more successful than initial strategies proposed. This is because the long short-term memory is or the LSTM cell brings about an element of memory to an NN cell. So this is achieved by maintaining a special element called the cell state, and also there are a few more components called the gates. So we will discuss about all of this shortly. And here, unlike the leaky units, the weights for the gates or weights for the self connections are learned through the training process. Now let's discuss LSTM in detail. So this is how a normal standard RNN cell looks. So the computation involved to compute the output is straightforward. It's just an activation function applied on the fan transformation on current input and output from the previous time step and a bias. With LSTM, there are a few more computations involved. It's just a more extensive set of matrix operations. Now the RNN cell in an LSTM network is replaced by an LSTM cell which consists of these components too, which the input gate, the output gate, forget gate, and the cell state, which is the most primary concept. Now the cells, this is the cell state. The cell state consists of all the learning that is retained up until now. The cell state is what retains the learning in every time step. And the gates are just elements, gates are just elements which decides what amount of information goes into the cell state or out of the cell state. It's just another series of matrix operations. Now we'll look into each of the gates in detail. The forget gate. The forget gate is the gate that controls or decides which all information from previous timestamp has to be thrown away and which written. So it basically limits the amount of information that should flow from the previous cell state in previous time step to cell state in the current time step. Every gate outputs a value between 0 and 1. This means that if the value is 0, then for forget gate, the cell state information from the previous time step can be completely discarded, and if the value is 1, then the cell state information is completely retained, and any value between 0 and 1 means that the information is partially retained. Now the forget gate is computed. Forget gate is value is computed again over the inputs and the hidden state outputs from previous time step. The I indices the cell. Indexes the cell. So let's say this is the network that we are considering. So let's say this is the ith cell, and J corresponds to the neurons in the previous layer from which the output from which the input X is coming towards the ith cell, and Uij corresponds to the weights between these connections. So this is the summation, this is the matrix, U is the weight matrix corresponding to these connections, and Xj is the output of these all J neurons. So this is the summation over Uij times Xj, and this is the output from the previous time steps, and J here corresponds to the outputs to the neurons in the these J neurons in the next layer, so, and from the previous time step. So, and these are the weights corresponding to those connections. So it's the summation over all J weight times output from the previous time step, and this is the bias associated with this particular cell. And then a sigmoid activation is applied on the output of this transformation. So now this will output a value between 0 and 1. So this is forget gate. Now the input gate. Input gate controls the amount of information that should flow from the current that should flow into the cell state from the current input. This is again computed over the current input and the output from the previous time step, and the indices are similar to those that was mentioned for forget gate, and it again, this is the bias associated with the particular neuron for the input gate. So there is a bias associated separate bias associated for each of the gates, and weights again are also separate for each of the gates, and the activation is further performed just like forget gate over this transformation. Now the current cell state. The current cell state further is updated using the output of the forget gate, output of the input gate, the previous cell state value, and the current candidate. Current candidate is computed as activation function computed as very similar to computation of transformation of input gate or forget gate. So this is again the input values, and these are the output from the previous time step, and these are the weights associated with them, and this is the bias associated with and the activation performed over it. So this is the current candidate, current input candidate, and this is the fraction which limits the amount of current input that should flow into the current cell state, and this is the fraction which limits the amount of previous time cell state from previous time step that should flow to the current cell state. Now output gate. Now it is not necessary that all of the whole of the output of the current state be predicted out as output. So to limit the amount of output that flows out as the prediction, an output gate is used. So output gate again performs a similar activation function on the transformation of the inputs and the output from the previous time step, and then a tanh activation function is performed on the current cell state, and it is limited by the output gate's value. Now this is how the whole picture looks. So at every time step we have the prediction from the previous output value or the prediction from the previous time step, and a new information which flows into each of these gates. This is the output gate, it's also called the selection. This is the forget gate, and this is the input gate, and the prediction from the input gate flows through, all the possibilities flows through here, and this is where the cell state is maintained, and after updation of the cell state, the output passes on to the output prediction, before which it is limited by the output of the output gate. This is how the whole picture looks. Now let's walk through an example to understand it in a better depth. Let's say we have to write a children's book, and these are kind of sentences that we see in a children's book. Spot so Doug, Doug so Jane, Jane so Spot. So if we used a RNN to perform this prediction task, the problem is that RNN does not really, the RNN is unable to maintain preserve long-term dependencies. So as for RNN, all that it knows is that a name should be followed by a period or saw, and saw should be followed by a name and name. So according to RNN, Doug period or sentences like James or Jane are all valid. So it would output sentences like this, which is wrong in this context. So let's say how LSTM overcomes this. Let's say we have an LSTM which is completely trained with enough training examples, and all the weights have been learned so far. All the weights to the input gate, output gate, forget gate, and the activations are all the input gates have correctly learned the weights. So far, let's say this has been the output Jane so Spot, And now let's say this is the current input duck. So since the previous output was period, so the viable predictions are duck, Jane and spot, and the current input is duck. So we have two vectors which is passed on to all three gates, all three of these gates. So the gates have already learned the weights. So here the gate would now predict that possible output for this possible prediction for this input is saw. So the word saw will be predicted with a positive vote. But it also learned that now that Doug has the word Doug has been seen, it is very much less probable that the word Doug will be seen again in very near future. So along with the prediction of saw with a positive vote, it also outputs the word Doug with a negative vote. So both these words will propagate towards here, and this is where the cell state is updated with these values. Now also the output the inputs flow through the forget gates through these updations also occur here. Now from here the words duck and saw flow forward, and the selection gate will now know that saw ducks should be discarded here, it has a negative weight. So the word saw will be predicted as the output. Now at the next time step we have the prediction duck, saw, and the current recent information as saw. So these two vectors again pass to each of these gates. Now this input gate will make a prediction. It knows that the recent information is saw. So the output can be either of duck, Jane or spot. So these three possibilities passed forward here. Now at this point the previous cell state had maintained the value maintained the values saw and duck, saw with a positive weight and duck with a negative weight. Now when this forget cells current cell state is updated with the previous cell state and the current input, duck gets both a positive weight from the current cell state current input vector and a negative weight from the previous cell state. So it cancels out and it's not propagated forward anymore. Now so this is disregarded here. So at this point the prediction will be just Jane or spot. Both are valid outputs in this context. So with this mechanism, LSTM prevents itself from predicting invalid outputs or outputs which are out of context, such as duck period or Jane saw, Jane period, etc. So this is how LSTM works. Now let's see how LSTM learns its weights. So let's discuss the procedure of back propagation through time in LSTM. So now we know that these are the forward pass values for LSTM. This is the current candidate. It is a tanh function over current input and times the weight and the output from previous time step times its weights. And this is the input gate output, forget gate output, output gate output, and this is the current state updation equation, and this is the output gate updation equation, which is limited by the this is the prediction output which is limited by the output gate value. Now let's ignore the nonlinearities and define ZT as a vector of all these components AT, IT, FT and OT, and ignoring the nonlinearities we define it as the matrix product of the weight matrix WC, WI, WF, WO corresponding to each of these components, and UC, UI, UF, UO times XT, HT minus 1, which is the input to the current time step, which is current input and the output from the previous time step. Now the most straightforward computation is the gradient for the final output. Let's say we have T time steps. So the gradient for HT or the final output can be directly computed because error itself is computed using the output of the final neuron. So derivative of error with respect to derivative of HT is just straightforward computation. Now given this we know that HT is computed using this equation OT pairwise product tan H CT. So we can compute the gradient of OT and gradient of CT using this equation, using the chain rule. So derivative of error with respect to derivative of OIT is just the derivative of E with respect to derivative of HIT, which is nothing but the gradient of HIT, times derivative of HIT with respect to derivative of OIT, which we can observe that nothing but tan HT, tan H of CT. Now for CIT again it is the derivative of E with respect to derivative of HIT times derivative of HIT times derivative of CIT. So here we from this equation we can observe that it is the derivative of tan H of CT, and derivative of tan Hx is 1 minus tan H square x. So it is OIT, which is a constant with respect to CIT, OIT times 1 minus tan H square CIT. So this is the gradient for CT or the cell state, the I corresponding to one particular neuron, and without I it is for the whole layer. Now we know that cell state is updated using the equation CT is equal to IT pairwise product times AT plus FT, which is the forget gate times output from the previous cell state from the previous time step. So gradient for IT, AT, FT and CT minus 1 can be computed here using the gradient for CT which we computed earlier. So for gradient IT, it is again the chain rule, derivative of E with respect to derivative of CT, which is gradient CIT computed earlier, and derivative of CIT with respect to derivative of IT. Now we can observe that from this equation it is with respect to IT, so this term is a constant here and so it is 0, and derivative of CT with respect to IT will simply be AIT with for this particular neuron, and for the whole layer it will be gradient of CT pairwise product AT. Now similarly for FIT, this term will now be a constant because it is with respect to FT. So this is gradient of CIT times CIT minus 1 because it's just the gradient derivative of CT with respect to FT, which is just CT minus 1. So this is it. And now for AT, again this part is a constant and its derivative is 0. So derivative of E with respect to derivative of derivative of E with respect to AIT is derivative of E with respect to CIT, which is gradient CIT, and derivative of CT with respect to AIT, which is nothing but IIT. And finally the gradient of CIT, which is derivative of E with respect to CIT minus 1. Now this part is a constant and it reduces to 0. So derivative, this part derivative of CIT with respect to CIT minus 1 is FT. So the final equation is gradient of CT minus 1 will be gradient of CT pairwise product on FT. Now we have the gradients corresponding to all the 4 of these outputs, and we had earlier defined ZT as a vector of these 4 components AT, IT, FT and OT. So gradient of ZD will be a gradient of these vector of these gradients. Now why we are computing all these gradients is because we can observe that the gradient what we have to update is the weights and the biases, but the weights gradient for weights or bias cannot be directly computed because they appear inside these activation functions. So we have to compute the gradients of these components first before proceeding to compute the gradient of these weight vectors and biases. So now that we have the gradients for all these components, we know that ZT has been defined as the matrix product of WO and IT, where IT is just the input vector. So we can now compute the derivative of IT as gradient of IT will be just the W transpose into gradient of ZT, because this is just the derivative of ZT with respect to IT, which is nothing but W transpose. Now gradient of HT minus 1 can similarly be computed using the relation IT from this. This has to be computed because gradient of HT minus 1 has to be propagated back to the previous time step, and it can be retrieved from gradient of IT. Now for the weight, the gradient of WT can be similarly computed by using gradient of ZT times ITT. This because gradient of derivative of error with respect to derivative of error with respect to weight is nothing but derivative of error with respect to z times derivative of zt with respect to weight. Now derivative of error with respect to zt is gradient of zt, and derivative of zt with respect to weight is nothing but it transpose. Now similarly, the gradient for biases can also be computed. It would look something similar to this. Now this is for one time step. So when we have t time steps, when the input is x1 through t uppercase t, the gradient will be a summation over all time step starting from 1 through t. So this is a summation over all time steps starting from 1 through t, gradient of wt, where t is the that particular time step, and the gradient for biases is also summation of all gradients for all time step from 1 through t. That's about it. Thank you.